Yeah, good evening from Japan. My name is Makoto Ando, a PhD student in the University of Tokyo, and my poster is about my current study, the search for protocluster cores, that is the most massive halos in the protocluster. What we did is, firstly, we extract massive galaxies from the photo-Z catalog of a large survey by Subaru telescope, and then estimate the halo mass of the massive galaxy by the clustering analysis and confirm they are hosted by the very massive halos, which can evolve into the redshift 0 clusters. And after that, we finally select about 2,000 protocluster core candidates. And then we calculate the overdensity and the red fraction around the core candidates. And we found the only cores with the red centrals shows the red fraction excess. So it's, I think, very interesting. So please come to my poster, number 3. Thank you.
Hello. So this poster is about the QSAGE HST GRISM survey. So this was a survey to look at the CGM along the lines of sight to central bright UV quasars. But in this, we found redshifts all the way along the line of sight to these quasars. And what we found is that the most UV luminous quasars at redshifts 1 to 2 live in dense environments. And we find that 8 out of 12 of our quasars are in significant overdensities. The most massive of these is PG0117 at redshift 1.5. It contains 36 members within a delta Z of 0.0125 and within a radius of 700 kiloparsecs. And this thing has a halo mass of greater than 10 to the 14.7. And so this agrees with the prediction from feedback moderated growth of black holes that says that your brightest quasars should be in your most massive dark matter halos. And in the diagrams here, you can see the redshift distribution, and then you can see here the quasar in the middle is the diamond, and then all the galaxies at the same redshift as it are around it. And as I say, that's within 700 kiloparsec radius. On the right there, that's a stack of all of our galaxies along the lines of sight to our quasars. Okay, yeah, and you can see my paper down below and the poster obviously here, and the link to the paper is at the bottom.
Hello, everyone. I'm a postdoc from University of Science and Technology of China. My poster is focused on the 2 radio AGNs found in a complex proto-structure at redshift 3.3 in the 3CVO survey. Using new spectra from 3CVO, we found this proto-structure contains several overdensity peaks. The 2 radio AGN are hosted by either the brightest or the most massive galaxy in this proto-structure. Thus, by definition, the progenitor of BCG. However, the most massive galaxy is not reside in the main peak. This is an example of pre-processing that it has formed its most stellar mass before entering the main peak. We also found the 2 radio AGN hosted by different color hosts, indicating they're at different evolution paths or stages. Another main result is that neither of them reside in the most locally dense region and lacking nearby bright companions. That we propose merging may already happened in both cases. In the end, I want to advertise a poster from Brian Lamox and Denise Huang about the 3CVO survey.
Okay. Hello, everyone. I'm Yoshihiro Takeda from University of Tokyo. Now we are all intensively discussing protoclusters, but the complete opposite region, void, is also interesting. However, you know how difficult it will be to find a void in the highest universe. To overcome the difficulty, we developed a deep learning method. It is called VoidNet. VoidNet is training by millennium iteration and outputs the probability of being a void galaxy, even from photometric data. Finally, we found several plausible candidates of void galaxies at Z4 from the HSC data. This deep learning method can surely be applied to the search for everyone's favorite protocluster, and we are now looking into its application. The number of my poster is D6, so please come to see my poster to know more detail. Thank you.
Thank you. Hi, everyone. I'm Keita Fukushima, a first-year PhD student at Osaka University. We study star formation and chemical abundance evolution in the protocluster region at redshift from 0 to 10 using the cosmological SPH simulation code GAJET3 Osaka. The left figure shows the gas column density of the protocluster region at Z equal 2. We define the extended region at the protocluster region and the central massive halo at the core region. The upper right figure shows the evolution of SFR in protocluster and core. SFR of each region becomes highest as densest different redshift. The bottom right figure shows the evolution of chemical abundance. We found in the core region, the effect of type 1a supernova appears after redshift around 3. This result is consistent with that star formation is more active in the core region. Yes, that's all. Thank you.
Thank you. I'm Kazuki Daikara, second year master student at the Tohoku University in Japan. I conduct a deep narrowband survey in the cosmos field. We obtained low mass star-forming galaxy down to about 10 to 8 solar mass. To study environmental effect, we compared two protocluster obtained by previous narrowband survey. We found many starburst galaxies above the main sequence at low mass end in the protocluster, while we do not find such a galaxy in the cosmos field. This suggests that some environmental effect may be work in low mass galaxy in high density region to enhance their star forming activity. Please visit my poster for detail. Thank you.
Hello everyone, I'm Kei Ito, a PhD student at the NLJ, and we present the poster with this title. And actually there are 3 points that I'd like to introduce here. So firstly, we are conducting a protocluster survey at redshift 4 by using a large data set of the HSC-SSP. And based on this protocluster survey, we found 180 protoclusters, and we are successfully deriving the less UV luminosity functions of the protocluster galaxies. So this is the figure that I derived of the UV luminosity functions. And these are based on these functions, we find protocluster galaxies have a higher star formation rate even at redshift 4. So if you are interested in one of these topics, please check our poster number 27. Thank you for listening.
Okay, hi, I'm Luwenjia Zhou. My work is based on the GOODS-ALMA survey. Our team has identified 6 optical dark galaxies in this survey. Here I show an example, AGS-24, the big red circle at the center of the pulse dams. It's extremely faint in the optical, but becomes visible at longer wavelengths. Optically dark galaxies are observed to be important contributors to the cosmic star formation history, and they show a contribution similar to that of galaxies in protocluster cores in simulations. And here, the bottom right is the density map of all the galaxies at redshift around 3.5. And we have all the evidence to show that 4 of the 6 optical dark galaxies, as indicated by the stars, lie in a large-scale structure at redshift 3.5. And you can check for more details in my poster. That's it. Thank you.
Hi, my name is Anisha Harrison. I'm a PhD student at the University of New South Wales in Sydney, Australia. And in this poster, I present our work on the effect of environment on star formation histories of protocluster galaxies at redshift of 2. So to measure the star formation histories of galaxies, we've used the Z-Fire and Z-Forge surveys along with legacy data and used the SED fitting code called Prospector. We find signs of environmental star formation suppression in the most massive protocluster galaxies, and we also find comparable star formation histories in illustrious TNG simulations. And to explore physical mechanisms that cause star formation suppression in massive protocluster galaxies, we use track the evolutionary history of galaxies in illustrious TNG. And we find that the most massive protocluster galaxies have had consistently lower gas fractions compared to the field galaxies since the last 1 gigayear of the universe. And so we hypothesize that the early signs of star formation suppression that we measure could be because of the inability of the galaxies to acquire more gas. Please find my full poster at B5 and feel free to interact. Thank you.
Yeah, bonjour, I'm Hervé Doll from Paris-Saclay. Thanks to Andrea Antony for accepting my ultra-late poster. The idea is to make an update about the Planck and Herschel survey we did a few years ago. And if you look at the two central plots, so from Marie Poletta and Yusei Koyama, some is not yet published, but will be eventually. You have on the middle plot a star formation rate versus redshift with a lot of plots of literature, and our one guy is the red star, where we have more than 1,000 solar masses per year of star formation. And thanks to the follow-up, spectroscopic follow-up, we are able to pinpoint every galaxy and see, for instance, that most of them at redshift 2.15. Sorry, I put it's 2.16, not 15. Most of the galaxies lie in the main sequence. And finally, which is the lower left plot, we try to make a constraint, as Roderick did in his very nice review, constraint on the mass halo versus redshift or plots. And I'm afraid we are still on the butterfly level, because adding one butterfly at a time takes 5 years to get a point, but hopefully we managed, and all the conclusions are on the poster. Thank you.